So last time we finished with the question, do all infinite sets have the same cardinality? Is there anything that's not countable? Is there just one infinity or are there many infinities? And surprisingly, the answer is that there are sets that are larger than natural numbers and larger and larger and larger. In fact, for any cardinality, there is a bigger cardinality. It goes off to infinity itself. The sets that are not countable are called uncountable. And in this lecture, we will use the technique called diagonalization due to Cantor to show that a set of real numbers behaves very different from a set of rational numbers, in the sense that there are way more real numbers than rationals. In fact, pretty much any number you could if you throw a stone into a number line, you hit an irrational number because there are way many of those than of rational numbers. And also you'll see a hint of why there are infinitely many different cardinalities, infinite cardinalities, in a proof that if we take a power set of a set, we are always going to get something larger than the original set. So if you take a power set of a countable set, it would be uncountable, and then we can build bigger and bigger and bigger set. Finally, what does it have to do with computer science? It actually relates to something very, very dear to programmers' heart, bug checking in software, because some of that ends up being interpretable as it is impossible to build a perfect bug checker. That's a very surprising thing, and it's very strange that we go from infinities of infinities to bug checking, but you will see how it goes. So, what is diagonalization? This is a technique that works as a proof by contradiction to show that there is no possible bijection, there is no mapping between two sets. And the way it goes is like this. So suppose somebody is trying to convince you that two sets are the same size. If they're the same size, there should be a bijection between them. If it's a bijection, it has to be one-to-one and onto, so every element from one set should be paired up with exactly one element from the other set. So if no matter what kind of function they give you, you could say, no, it's not a bijection because it didn't pair up somebody, or it paired up somebody with more than one element of the other set, then you prove that those sets are not the same size. So let's do it on a very simple, very finite example, and let's do it with a set of 3 elements and its power set. So here A, B, and C are just 3 elements of the set A. So suppose somebody is trying to convince you that there are exactly as many elements in the set A, which has 3 elements, as in its power set, which actually, if you count it, has 8 elements. You say, well, if you are convinced that they're the same size, then give me a bijection. They give you some function, and that function takes the first element of A and maps it to some set S1, which is a member of power set of A. It maps B to some set S2, a different set hopefully, and it maps C to yet another set S3. And now they're claiming that there is nothing in the power set of A except those 3 sets. How would you prove them wrong? So let's do it on an example, and you could see that no matter what S1, S2, and S3 they give you, your example, the same argument is going to work. So in order to do this example, we will construct a set which is not S1, not S2, and not S3, and yet it is a member of the power set of A. And here's how we are going to do it. First, we will think of set S1, S2, and S3 as represented by their characteristic strings. That is, they will be strings of length 3, the number of elements in A, with a 0 if the corresponding element is not in a set, and 1 if an element is in a set. So for example, the set S1, which contains just element A, will be encoded by the string 1, 0, 0, so A is in, B is not, and C is not. And now let's try to write them in a table. So the rows of the tables will be the sets that purportedly cover all the power set of A, S1, S2, and S3. And the columns will be those position indices which are labeled by the elements of A, which really just label the position in the characteristic strings. So for example, again, S2 is a set BC, so A is not there, that will be 0, and B and C are, so it will be string 0, 1, 1, and we could label the first, put the first 0 in the column labeled A, put the first one in the column labeled B, and the last one in the column labeled C. So now, how are we going to actually use it to prove anything? Let's take this table and look at its diagonal. This is where the word diagonalization comes from. So with the diagonal, we look at first element in the first row, second element, and the third element in the third row. And now let's build a new set, let's call it a D, which will be different from every set in the list in the element on the diagonal. So for example, the very first element of a set D will be different from the set S1 in the first element. So S1 contains element A, so D will not contain element A. So D is different from S1. Now S2, we don't want to look at element A again because it's different from set S1 and we cannot really say two different things, but let's look at the second element, B. So in order to differentiate D from S2, let's make it behave differently on the second element. S2 contains B, so D does not contain B. Finally, S3 does not contain C, so D will contain C. That makes D different from S1, different from S2, and different from S3. But it's an element of the power set of A because, well, it's a subset of A. It's something that's a subset of A, B, and C. It's a set containing just a C. Therefore, we just constructed a set which doesn't get paired up with anything in A by that purported bijection F. That means that F is not a bijection. And no matter what S1, S2, and S3 somebody is going to give you, and no matter even if the set A is countable, you could do the same thing and argue that here's something that didn't get paired up, so whatever function you are thinking of, it was not a bijection. So let's use it with something slightly more infinite and use it to show that the set of all real numbers is uncountable. Moreover, we will show something stronger, that not only there are uncountably many real numbers, there are already uncountably many real numbers between 0 and 1. So we will include 0, but will not include 1. For that, we will think of a real number between 0 and 1 as 0 then decimal point, and then infinite sequence of digits. And this is one of the possible definitions of real numbers, that this is a number, then decimal point, then potentially infinite sequence of digits. And it has to be infinite because if it's finite, we are not going to get all the real numbers. In fact, we will get just rational numbers. And having infinitely many of them is crucial for this proof to work out. Now, let's use diagonalization to prove that the set of all real numbers is uncountable. Again, let's do it by contradiction. Imagine that there was a list of all real numbers between 0 and 1. So there is a A1, which is the first real number, A2, which is the second, and so on and so forth. And let's, when we are looking at a real number, use this notation to talk about the first digit after decimal point, second digit, third digit, and so on. Now, just like we made a table where rows were labeled by first thing, second thing, third thing, S1, S2, S3 in the previous example, here we will label rows by A1, A2, A3, which are reals in our list that supposedly count them. And how are we going to label columns? We will label them by digit, by decimal places. So the first column will be the first digit, the value of the first digit after the decimal point, second column the second digit, and so on. You could see that if you just write numbers one under another and more or less align them, you could always pinpoint those columns. Now, let's use the same argument to build a number d, which is a valid real number, but which cannot possibly occur in that list A1, A2, A3. And that will show us that if that list was created by some function, that function must not be a bijection because it missed the number d. It didn't assign any natural number to a number d. And here's how we are building d. Let's take the diagonal of this table again, and let's make d to be different from every number in the list in the diagonal element. And a simple way of doing it is just to say, if it's less than 9, let's make it 1 greater, and if it is 9, let's make it a 0. So for example, in the first if the first number in our list has 2 as the first digit after the decimal point, our number d will have 3. If the second number has a 0 as the second digit after decimal point, we will put a 1. If the third number has a 9 as the third digit after decimal point, we will put a 0, and so on. So now we got a real number, which we represent as a sequence of digits, infinite sequence of digits. So why would this number not be in the list? Suppose it is in the list. Let's say it's the same as the number a sub k. But wait a moment, let's look at what's happening at the k's decimal point. And by the way, if your number stops somewhere, that just means that all the rest of digits are zeros. So, for example, 0.3 is 0.300000 off to infinity. So anyway, let's say the d is the same as number a sub k. But then let's look at the digit number k. It should be different between the number a sub k and the number d. So no matter what k you pick, there will be some digit where the two numbers have to be different, and this shows that d cannot possibly be in the list. That would be a contradiction. Since this works no matter what is the order in this purported numbered list of all reals, it shows that there is no possible bijection between real numbers and natural numbers, and the set of all real numbers is uncountable. Similarly, And closer to computer science, we could show that even though every language, a set of finite strings over a finite alphabet, is countable, like A, B star, binary strings, English, all Python programs, and so on, the set of all languages is uncountable. Even the set of all languages over the same alphabet is uncountable. So let's show that the set of all languages over the alphabet, which is 0, 1, binary alphabet, is already uncountable. Let's do it like this. Again, suppose we had a list of all the possible languages, all the possible sets of finite strings over the alphabet 0, 1. Let's label the rows of our table with those languages, language 1, language 2, language 3. Let's label the columns with strings, just like we did for the power set example. And here, let's just put, again, you could think of characteristic strings, but to avoid the confusion between binary strings and 0, 1s and characteristic string, let's say you put yes if a certain string is in the corresponding language, and no if the string is not in the corresponding language. So for example, the language L1 contains an empty string and a 0, but it doesn't contain a 1. L2 does not contain a 0, does not contain 0, 0, but it does contain 1, 0, 1, and an empty string, and so on. Now let's construct a language which is different from every single language in our table, again showing that whatever was the function that mapped languages to numbers 1, 2, 3, and so on to create this list, that function didn't map any number to that language D. And again, we constructed by looking at the diagonal of the table. So the language D should differ from the first language on the first string, which was a string that was an empty string, lambda. So empty string will not be in D. Now let's look at string 0 in the second language. Second language does not contain 0, so D will contain the string 0. Third language does not contain a 1, so D does contain a 1, and so on and so forth. And now it looks exactly the same as with real numbers. The language D cannot be language number K in this list, because what happens on the K string, on one hand, if the case language in the list contains it, then D shouldn't, so it should be different from there. So here is one interesting corollary of this. So this proves that there is no bijection between the set of all languages and natural numbers. That is, there is no bijection between the set of all languages and any countable set. Let's look at the countable set, which is a set of all Python programs. What it says now is that there is a language for which there is no Python program which would correctly compute that language. Which means that there is some language, can define some language, which is not going to be computable. There is a limit to what we can program, no matter how good a programmer you are. That's kind of disconcerting, but here is the thing. There are things, there are languages which are impossible to compute. So let's see an example of such a language. And this has to do with that bug checking software testing problem. So the halting problem was the problem that was identified by the famous British mathematician and one of the first computer scientists, Alan Turing, who essentially invented computers as we know it. And this is how he formulated it. So let's look at the language, at the set of a program and a string, which we could think of as an input to that program, such that that program stops if you run it and give it an input x. For example, your program may read its input, and if its input is a number, it will take a square of it and output that. And maybe if you give it a number 0, or you give it something that's not a number, it will go into an infinite loop and crash. So probe is a piece of code, and piece of code is, well, a string. So there is nothing wrong with thinking about a language which is a Cartesian product of set of all possible Python programs with a set of all possible, let's say, binary strings. So what makes it so special? Imagine that this problem was solvable. That is, suppose somebody can write a program called halt, which is German for stop, which would take a piece of code and a string, and it will always stop, and when it stops, it will say yes if the program stops when you run it with input x, and it will say no if the program will go into an infinite loop if you give it the input x. Now, suppose now you could take that piece of code for the program halt and do a little bit of stuff with it. So first of all, we will not give halt two different things, prog and x. We will just give it its own code as an input x. There is nothing wrong with that, because nothing would stop you, for example, from having Python interpreter written in Python and give the code for that interpreter to the interpreter itself. Why not? And the other thing that we will do, and again, this doesn't require us to know anything about the program called halt. We could just call it from some library if it exists, is the following. So if the program halt said yes, our program that we will call diag for diagonal will go into a loop and will never stop. It's very easy to go into an infinite loop. Just put some kind of statement, while 0 less than 1, just keep executing. Then it will never stop. And if the program halt says no, in this case you stop and output something, doesn't really matter what. Say yes or no or whatever. The crucial thing is that if you run halt on prog and it says yes, then the diag program will loop, and if it says no, then it will not loop, it will stop and output something. Since halt always stops, whenever it says no, the diag will always stop as well. Here's what happens now. Suppose you give the program for diag its own code. Nothing wrong with that. There is nothing in this program that one cannot do in your favorite programming language. So what would this program do though? Because if it stops giving its own code, then by its definition it should be looping. But if it loops given its own code, then by its definition it should stop. That's a contradiction. It's similar contradiction to the barber who shaves everybody who doesn't shave themselves. So what can we get out of that contradiction? There is no way such a contradictory program diag can exist. But we built it out of the program halt by using very, very simple statement. Well, the only way diag cannot exist is if halt does not exist. And what that means is there is no program halt that always stops and gives the right answer to the halting program. That means that if you want to do bug checking as simple as does this piece of code go into an infinite loop, maybe you could do it in some special cases, but if you want to solve it in full generality, that's not possible.